So we've gotten this base introduction to machine learning through a very simple example, but now I want to talk about regression, which is a type of supervised learning approach for machine learning. Regression is super popular. The applications are everywhere. And our simple example of the line of best fit was a regression problem, albeit with synthetic data. But essentially, over here, this was our scatter plot. We had our x variable here and then our y variable here, and we plotted this linear relationship between x and y. And we're trying to find that line that is the best fit, has the lowest error, the best predictor of these points. And we found it. And this is what we call a simple linear regression task. A simple linear regression task only has one x value. So we're just doing one x value in its relationship to y. We're going to get into more complicated ones like multiple regression, where you have not just one x value and how it relates to y, but 2, 3, 4, and in some cases in the world you have 10 to 20 and maybe more. And so you're trying to find the linear relationship between all of those points and your y value, and you're trying to fit a model to that data. And so regression is a supervised learning approach where you're trying to train model parameters to predict a continuous value. Some examples are house price prediction. You have the features of the house and you're trying to predict the price that it would sell at. The lifetime value of a customer. You have some features on that customer profile and their behavior, and you're trying to see how long this customer, you're trying to predict how much money this customer is going to make for you, how many products they're going to buy over their lifetime. Household income, you may have some features about the people living in a house, and you're trying to estimate their income. And those are some examples of applications. Some common cost functions are going to be the mean squared error, which you already saw. Mean absolute error, that is just going to be the absolute difference between the y true and the predictions without squaring it. So you just take off that square and only keep the absolute value of the difference. Residual sum of squares is going to be mean squared error, but without the mean part. So you just take the sum over all the square errors. You don't take the mean. You don't divide by n. Huber loss is a different one. Huber loss is kind of like mean squared error, except past a certain point, if your error gets too big, the error doesn't grow quadratically like a mean squared error. It actually grows linearly. I can encourage you to look up Huber loss. Huber loss is actually commonly used and is actually outperforms the others in some tasks. Two common accuracy measures are going to be the R squared and the adjusted R squared. So the R squared, just our R squared, is going to be the correlation coefficient squared between the predicted values on your data set and the actual values. And so imagine this was a plot not of the XY relationship, but of the relationship between the predicted values and the actual Y values themselves. If the predicted were exactly equal to the Y values on every single example, this would be a straight line of points all the way up, because every prediction would be equal to that Y value. It'd be a straight line of points. It'd be perfectly linear, and so the correlation coefficient would be 1, and so the square of that correlation coefficient would be 1 as well. And so for that reason, R squared is between 0 and 1. It's the square of the correlation between your predicted values and your actual values. And obviously, the higher those two are correlated, the better your model is predicting the actual values. Now, R squared is good to use if you have one independent variable. So we have X and Y relationship here for simple linear regression. R squared is a good accuracy measure. The problem is when you add in multiple X values. You're using multiple features to predict your Y value. So if you have X1, X2, X3, you have multiple features to predict your Y value. R squared needs to be replaced with adjusted R squared. And so adjusted R squared is still the square of the correlation coefficient between your predicted and your actual values, but it's penalized by using additional features in your model, additional parameters on those features. And so it's like Adjusted R-squared is going to calculate, like I said, the square of the correlation between your predicted and your actual values, and then it's going to penalize you for each additional feature that you used. And that's a way for us to balance accuracy and complexity of our models. And so that's regression from a high level. I'm going to hop right into introducing us to the data set we're going to use to learn regression on, and then we're going to hop into training a regression model on that data set.